Okay, so here's the data then, V and P, the volume and pressure. It's thought that it obeys this rule here, and we need to verify it, that it obeys this property here. PV to the power n equals capital C. And we need to work out the value of n and c for this particular law and these data points. So we're going to use data, we're going to draw a plot. I'll try my best with the digital pen and we'll work out these values. Well, clearly, let's take logs because we've got a power here. So log of the left hand side would be log p plus, and when you take log of v to the n, you can write that as n log v is equal to the log of c. So hopefully we can see the straight line relationship here, because we'll have log p then is equal to minus n log v plus the log c. So I've just moved that over. Here's y equals m x plus c, isn't it? So we can read off the correspondences. But the first thing we need to do is to plot log p against log v. Then the gradient will be the value minus n, and the intercept will be the value log capital C, and then we can get these values, can't we? So that's what we need to do. So let's take the data then, and we'll do log v on the x-axis and log p on the y, isn't it? So log 1, log 2, log 3, log 4, log 5. We're doing log to base 10 then. Log 1, which we know is 0. Log 2. Zero 0.3. Log 3. 0.48. Log 4. 0.60, and this was 0.30, wasn't it? And then log 5, 0.70. And then log p now, 204. Log 204, 2.31. 2.31. Then log of 115. 2.06. And then log 80. 1.90. And then log 64. 1.81. And then it's log 52, the last data point. Log 52. 1.71. 1.72, wasn't it? Yeah, 72. Okay, that's what we need to plot. Now I haven't got a ruler and graph paper, so I'm just going to use a digital pen here and do as best I can. So I'm just going to do it like that, if that's okay. Put in the axes, x and y. Okay, so first of all then, it goes up to 2 as the biggest value on the y-axis. So if we do 0.51, 1.52, that would be on our graph paper, of course. And 2, and this is the axis for log p, so that would be 2.5 up there. And this is log p. And then if we do log v and it goes along to 0.7, so 1, 2, 4, 5, 6, and this would be on our graph paper, of course. And then we could be nice and accurate with the entry of our data points. There's 0.7. This is log v along the bottom, isn't it? So the first entry data point 0.2.3. Then it's 0.3, 2.06. Mark that one off. I'll do as best I can, as I say, 0.48, 1.90. Somewhere around there. 0.6, 1.8. And then 0.7, 1.72. So I think that looks like it, as best as I can draw. So I'm going to try and draw the straight line now, as best I can. Going through the data points, like so. Now you can see the data points are just interspersed. It's only data. So basically the best thing to do would be to draw a conveniently based triangle. So I'm going to draw one down from 0.1. I'll make an estimate. Come down and go across here. For example, so let's come across here. Oops. It's got to be a straight line, horizontal line, and you'll need to be as accurate as possible. Nice generous triangle here, which is not great. I should have gone along at 1.5, shouldn't I, really? Because I've gone off the scale of the graph, really, on the bottom, so I can't measure it. Okay, so let's go across the bottom, 1.5, go across here, say. That's convenient. .5, what value was that? That was 1.72, so this should be well below. So I'm going off kilter here, aren't I, with the triangle. Let's go down like so. There we go, that's it. So there and there. So the vertical distance, you'd read off the difference between this height here to here, 1.5 to say 0.8 roughly. I know mine isn't accurate, and this one is 0.1 to 0.8 is 0.7, I would say. I would hope that you would get a much better measure with a graph, because you can measure it so much more accurately than this approximated graph on with the digital pen. So here the gradient, then we can read off the gradient. M is increase in y is minus 0.8, so it's going down. Increase in x goes across 0.7. So 0.8 divided by 0.7, 1.14, so it's minus 1.14. The more accurate in the table, yeah, they've gone along to 0.9 here, so that would be 0.9. So I'm going to change that because my reading is way out from what's done on the plot example. So I'm going to change that to 0.9. That should have been probably more accurate reading there. So let's try that and see if I can get something that's approximately right. Accurate enough. So let's change that to 0.9. Sorry about that. Minus 0.89. So that would be minus 0.89 then, wouldn't it? So there's our gradient then. In the notes they come out at minus 0.84 on the tabulated formal graph version. So okay, so we got m, which is minus n. And then we can read off the intercept from the graph, can't we? Which looks like this one looks to me like 2.4. That's what I would put as the intercept. But this point actually does go through it very accurately, so we're going to use the original data point 2.31 as our intercept. So C equals 2.31. So let's go back to the original then with our values minus 0.89. So N equals, wasn't that right now? M, which is minus N, equals minus 0.89. And log C is equal to 2.31. So this is log base 10 we've been doing, haven't we? So C, shift, the 10 comes up, hits that in the air, it's 10 to the 2.31. So let's put that in the calculator. 10 to the 2.31. 204.17. 204.17. And here on the above, you can see, run the minus through, you get n equals 0.89. So that we've got these values then from the graph. So we can see that PV to the n, so P times V to the power n 0.89 then. This is the law. that we've got from the observed data is equal to 204 for this particular gas, 0.17. And we could use that when we're looking at the problems involving this gas and this problem.